Hello everyone. Today we will continue the module 9 liquefaction, and this is the second lecture on liquefaction. Before we proceed, let us quickly go through this video which I have also shown you in the previous lecture, and this will help you to recall what exactly is the liquefaction. So basically liquefaction is the state or condition of the soil when it does not hold the load, right? And then it fails. So because of that we call it liquefaction, and this particular video will try to help you to understand how a liquefaction occurs. So if you just see this video, here you have loose granular sediment, and then you have strong shaking. So this is the layer of granular sediment, and then you have the groundwater which is saturating this particular layer, and the same time you have this earthquake, right. So we also discussed about the earthquake, and here this is the situation when it fails, right. So this is the example from San Francisco, and it was occurred in 1906, right. So before we proceed, let us try to understand why a particular soil fails, or whether all the soil fails. So what is this different scenario under which a soil fails, right. So that's why, is the soil susceptible to liquefaction? That is the first question. And if the soil is susceptible, will liquefaction trigger? So susceptibility is one thing, but actually if liquefaction is happening, that is another thing. So here we have these points that we need to analyze for our soil. So the presence of soil, whether the strata is having the soil layer, right, because we are talking about the liquefaction which is possible in the soil column, right. So the first one is presence of soil. So and the second one is age of the soil deposit, whether it is newly formed soil, right, or whether it is a old one. If it is newly formed, if it is a newly formed deposit, then what will happen? This will not be compacted, it will be loose granular, right. And then what type of grain sizes are present here, what type of soil is present here, that is equally important. Then what is the topography, whether we are talking about the elevated areas, whether we are talking about the flat lands, that is also important. Then history of seismic events, whether this particular area had any earthquake episodes, or whether any particular location has shown the liquefaction behavior, right. So this is very important, what is the history of that area. So when we talk about the liquefaction susceptibility, not all soils are susceptible to liquefaction, right. If a soil is not susceptible, further hazard analysis is not required, and if it is susceptible, we will go for the complete analysis. So when it is susceptible, a stress based approach is used to evaluate the factor of safety against liquefaction. Now we will try to understand all the parameters and all the details about the stress based approach, right. So we will go one by one, and we will try to understand each and every component about the liquefaction. Now when we try to see the liquefaction susceptibility criteria, we have historical criteria, then we have geological criteria, and then we have compositional criteria. So when we talk about the historical criteria, we try to refer the historical information, and here we will try to refer to the geological information. And the compositional, that means what is the behavior, what are the properties of that particular soil, right. So when we talk about this historical criteria, it has been observed that liquefaction repeatedly occurs in the same region. So, in the same area we can expect again there is a episode of liquefaction. This historic data sets is used to develop different models to assess liquefaction susceptibility of a soil. So, once we know that if this is the area and these are the locations of liquefaction, right, then we can have all the parameters of these locations that we will discuss, and then we will try to train our model so that for any given new location it will try to assess whether it is susceptible or not susceptible. So, that is with the historical data. The historic data sets are shown liquefaction reoccurrence within a particular zone. So, this zone we are trying to analyze here. Worldwide data of liquefaction occurrence collected by Ambresi et al. 1988 shows there is a particular epicenter distance within which liquefaction tends to occur. So, suppose if this is the area and this is the epicenter of the earthquake, so we will have different distance from this, and there is a particular distance from which this liquefaction is possible. That is being analyzed by this researcher, right. So, here you can see the epicentral distance to farthest observed liquefaction feature, this is in the kilometer, and earthquake moment magnitude. So, he has drawn this particular line based on all these data set, that if the points are falling in this region and this region, their behavior will be different. So, if the point, let us say I have a location which is 10 kilometer away from the epicenter and the moment magnitude of the earthquake was 7. So, where it will be? It will be here, right. So, this is towards the liquefiable. So, this is the liquefiable zone, right. This is non-liquefiable zone. So, if my points are falling in this, immediately we can say that this particular location is having the susceptibility of liquefaction. So, here it is written non-liquefied locations with epicentral distance and magnitude taken from Ambresi et al. 1988 in this particular paper, right. And here they have nicely given this particular line, and this line segregate or separate liquefiable zone and non-liquefiable zone. So, this is the equation of that particular line which we have just seen. So, here you can see for this particular line we have this equation, right. So, this is the moment magnitude, and here RE is the distance of the site to the epicenter of an earthquake. So, this is very important, earthquake magnitude epicenter relationship that defines or that will exactly say whether your location is liquefiable or non-liquefiable. Then comes the geologic criteria. The geologic environment for liquefaction susceptibility is very much narrow and specific. So, that means there are very certain parameters which triggers the liquefaction, right. So, this susceptibility is very narrow and specific, that is stated by Yod 1991. This includes the hydrological setting. So, what is the hydrological condition of that particular area? The depositional environment. What are the depositional environment? Because we are talking about the geological criteria, and the age of the deposit. I mentioned this in the first slide, that age of the deposition also tell you what is the compactness of the soil, right, and what is the depositional environment, what is the hydrological setting. Then comes uniform soil produce more susceptibility. That means if you have one type of soil with one type of grain, what will happen? They will be more susceptible to failure or this liquefaction. Why? Because they will have pore spaces that will be available for this water, right. When you have different gradation, what happens? These pores are filled with this fine grains, right, and then this particular soil will not be susceptible. So, that we will see in the other part. So, here it says the geological process manifesting uniform deposits in turn produce liquefaction susceptibility. So, we need to be very careful about the hydrological setting, depositional environment and age of the deposition. Then liquefaction is more observed in fluvial, colluvial and aeolian deposit. So, here the fluvial deposit, sediments transported and deposited by rivers in a continental environment, that is fluvial. Then colluvial, sedimentary material that gathers on slopes within caves or in rock shelters. Then comes the aeolian, sediments such as sand, silt and clay that are carried and laid down by wind action. So, that is the characteristic of aeolian deposit. So, these three types of deposits are having more probability of liquefaction. Soils from Holocene. So, the Holocene is the most recent one. If you see the different time frame of the geological periods. So, here Holocene period are more susceptible to liquefaction compared to those from the Pleistocene period. So, when we talk about the Holocene, often found in low lying areas such as floodplains, deltas, coastal regions, these soils are more likely to be saturated with water, because water plays a significant role here. High water content increases pore pressure during seismic shaking, leading to liquefaction, right. And when we talk about the Pleistocene, typically located in older, more elevated terrains, these soils are often dried and less saturated, because we are talking about the elevated regions, reducing the likelihood of pore pressure built up and liquefaction. So, that is the major difference between these two. So, Holocenes are more susceptible to failure or liquefaction. Human made soil deposits, like because of the anthropogenic activities we are having soil deposits, also need attention. Uncompacted loose fills in particular are highly prone to liquefaction, because they are not compacted, and during a seismic event there will be shaking, and if there is a water availability, the groundwater is nearby, then you will have more chances to liquefaction. The stability of hydraulic dams and mine tailing piles, where soil particles are loosely deposited through water sedimentation, continues to be a significant modern seismic hazard. Well compacted fills are unlikely to liquefy, though it is man-made or anthropogenic activities are involved in this, but this is having very less likely to fail, right. When we talk about this compositional criteria, so we have two things: excess pore pressure and the volume change. Liquefaction susceptibility depends on the development of excess pore pressure, which is influenced by compositional traits affecting volume change behavior. For example, you just imagine, it is not related to liquefaction, but there are certain clays which has tendency to expand. So, whenever contacted with water, they expand, the volume changes. Similarly, certain types of soils, they expand their volume, and when they expand, the compactness will be less, and during that time, if you have seismic events, that particular deposit will have the high potential to liquefaction. Volume change potential and susceptibility. Compositional features linked to high volume change potential generally correlate with increased liquefaction susceptibility, right. Then here from this we can say that key compositional characteristics are particle size, particle shape and particle gradation. So, when you are having different types of particle size or you have very good distribution of particle size, then you have less vulnerability to liquefaction. When we talk about the particle shape, if you have similar grain sizes, you have higher potential to liquefaction. When you have rounded, triangular or irregular shape, they will help to get this particular deposit compacted. So, similar type of shape will be more vulnerable to liquefaction. Different types of shape available in a soil will be less susceptible to liquefaction. And similarly, this is the gradation. So, distribution is good, then you will have less susceptibility to liquefaction. So, this is one of the very widely used criteria. This is called Chinese criteria. So, this is given by Wang et al. In 1979. So, he proposed this particular graph, and here you can see this line is basically separating the liquefiable and non-liquefiable zone, right. So, this is the part where it is liquefiable, right. So, understand it carefully. So, this part is liquefiable and this part is non-liquefiable, and this is separated with this particular line, and the equation of this line is W is equal to 0.87 liquid limit. So, here in the x axis you have saturated moisture content, this is the weight percentage, and here you have y axis liquid limit, this is in the percent. So, this line is having the equation W is equal to 0.87 LL, LL is the liquid limit. Now, here you can see this part is non-liquefiable, right. So, here W is less than 0.87 LL or LL is greater than 33.5. So, either it is less than this particular equation, right. So, W is equal to 0.87 LL, that is separating these two zones, and again if the liquid limit is more than 33.5, that will again be non-liquefiable. So, that is the criteria here, or the clay fraction is greater than or more than 20%, or the plasticity index is greater than 13. So, these are the criteria that you have to check for your soil before you go for the hazard analysis. If your points are falling in this region, your deposit or your soil column is safe. If they are falling in this, how you will check that? That using this clay fraction is less than 20%, plasticity index is less than or equal to 13, or W is equal to 0.87 LL, less than that it will be non-liquefiable, more than that it will be liquefiable, and the liquid limit greater than 33.5, that is non-liquefiable, less than this it will be liquefiable. So, this particular method is widely used to assess whether your soil column is having the potential of liquefaction or not. So, when we talk about this weight percentage, so that is calculated using this equation. So, where W is the water content and it can be obtained in lab by use of oven, drying, right. Now, when we talk about Pi, which is the plasticity index, that can be calculated using the liquid limits and the plastic limits, right. So, the liquid limit of a soil is the moisture content at which the soil transitions from a plastic to a liquid state, and the plastic limit is the moisture content at which a soil transitions from a plastic state to semi-solid state. And the plasticity index, the Pi, is a measure of the range of water content over which a soil remains in a plastic state. It is calculated as the difference between the LL and the PL. So, we are using the liquid limit and plastic limit to calculate the plasticity index, and that is very helpful when we are using this Chinese criteria to assess our soil whether it is susceptible or not. The clay fraction of a soil refers to the proportion of soil particles that are smaller than 0.002 millimeter or 2 micrometer in size, right. And the clay particles are the finest fraction of soil and play a significant role in determining the soil's physical and engineering properties such as plasticity, cohesion and water retention. So, this plasticity we have already seen in the previous slide. The cohesion, basically how cohesive is the grains of your soil, right. If you have more water content, the cohesion will be reduced. And what is the water retention capacity of your soil? That is also needed to evaluate the properties of your soil. Then, other than this Chinese criteria, we also have Andrew and Martin criteria. This is proposed in 2000, and here according to this criteria, the potential liquefiable soil will have less than 10% clay fraction and less than or equal to 32% of the liquid limit, right. And for the non-liquefiable soil, the clay fraction is greater than 10% and the liquid limit is greater than 32%. So, other than Chinese criteria, this Andrew and Martin criteria is also being used to initially evaluate whether your area is having the susceptibility to liquefaction or not. Then we have this Suchida criteria that is also proposed in 1970. So, here range of grain size distribution for liquefiable soil is used, right. So, x axis is having the particle size and y axis is having the percent finer. So, how much percent is present. When you see a particular soil column, right. So, here if you have different types of grains or different types of soil, right, then we assume this is very good and it is safe and liquefaction is not possible, right. So, if you assess the particle size distribution of any soil, if it is falling in all these region, which is also having silt, sand and gravels, and the particle size is also changing, the percent finer is also changing. So, in this situation, this particular soil is not susceptible to failure. But if a soil column has only one type of material, right, only sand or only gravel or only silt, right. So, in such situation, these are susceptible to failure. Why? Because they will not be compacted when there is a seismic event. When you are having the shaking because of the seismic events and you have different types of grains present in this particular soil, they will get together and they will be compacted, right. So, that is the basis of having this Suchida criteria. So, this is also one of the alternative other than your Chinese criteria to evaluate the potential of your soil to be liquefied. Is the soil susceptible to liquefaction? Using the previously explained methods like Chinese criteria or Suchida method or Suchida criteria, you can assess whether your soil is susceptible to liquefaction or not. If it is liquefiable, then we go for the evaluation of liquefaction potential. If not, then no further evaluation is needed, right. So, when we are going for the further evaluation, by chance if it has come to the liquefaction zone, then we can have all these parameter: earthquake intensity, earthquake duration, building load, then groundwater table, depositional environment, aging and cementation, confining pressure, then drainage conditions, soil type, soil relative density, particle shape, particle size distribution. All these will be used to assess whether your soil is having the susceptibility to liquefaction or not, right. So, when we talk about all these parameters, some of them can be measured in the field, that is in situ measurement, some of them are measured in the lab condition, right. So, laboratory based method, we have the cyclic triaxial test. So, we talk about the cyclic loading is simulated. In cyclic triaxial test, cyclic loading is simulated and the response of soil is reported, right. The number of cycle for liquefaction initiation is observed here. Now, we will try to see at what cycle this liquefaction occurs, right. So, the number of cycles will be noted here. Then comes the cyclic simple shear test. So, here this is the cyclic simple shear test cell. This is from the Yu et al 2024, right. So, it says shear stresses induced by seismic waves in simulated, which is more realistic than the triaxial test, right. Stress strain behavior is also noted here. So, that is being used for further analysis to liquefaction, right. Then comes the resonant column test. So, here the dynamic properties of soil such as shear modulus and damping ratio, which is critical for liquefaction analysis, are evaluated. So, this is a typical resonant column test. The shear modulus and damping ratios are derived from the resonant frequency and decay of vibration, which is used in liquefaction potential analysis. So, these are the methods or these are the instruments used in the lab to evaluate the potential of liquefaction for a given soil, right. And the soil will be collected from the area which has shown the properties and it has come into the liquefiable zone, maybe using the Chinese criteria or maybe using the Suchida criteria or maybe some other criteria, right. And then we are moving towards the characterization. Then we also have shake table test. Ground shaking is simulated here and the soil's response is observed under more realistic condition, right. So, here you can see the diagram of shake table apparatus. Direct observation of liquefaction behavior is done under simulated various seismic condition. This will provide you the input to analyze whether your soil is liquefiable. This is another one which is called SPTN. When we talk about the laboratory based method, these are very hectic. You have to visit the field and you have to collect the sample and then you have to analyze various parameter. You should have access to these advanced instruments, then only you will be able to study liquefaction, right. To overcome this challenge, Seed and Idris 1971 came up with the stress based approach that I will be discussing in the next few slides. in this approach, they correlated the liquefaction potential to standard penetration based end result SPTN, right. This was done because SPTN is very common in geotechnical engineering studies. Now, since we have seen the instrument which can be used in liquefaction potential evaluation, these instruments are not really available to everyone. So, to have an alternative, we thought of, or this Seed and Idris have thought of having another parameter which can be evaluated easily, right. So, for that they have investigated this SPTN value, whether we can utilize it for the evaluation of liquefaction, right. So, this SPTN is very common property which is measured in a geotechnical investigation. So, it is very common one. So, that is why this has been investigated to find whether it has any correlation with the liquefaction, right. So, we will discuss this further in the second part of this lecture. So, this is the first part, we are ending it here. So, thank you very much.